professor in the College of Sri Venkateshwara, University of Delhi for 1 year. And in 2017, he joined the Scientific Analysis Group, DRDO, which works in the field of cryptology. His primary area of research is code-based cryptography, and he is pursuing his research in the same area. And he has published 10 research papers and a book on cryptography. Welcome, sir. Please, stage is yours.
Thank you for the nice introduction. Hello.
I think all of you have a schedule in your hand. We have a very excellent lineup coming today. So we have basically 4 speakers.
Previous 2 talks. So with this I begin. Firstly, I think most of you won't be knowing that DRDO works in the area of cryptography as well. Actually, solutions to defense forces for their cryptographic needs. And as all are moving to post-quantum settings, so we have also a team working in area of post-quantum cryptography. So the contents that I will cover are some basics of cryptography and its classification, and what are the latest updates in quantum computing, what are the cryptographic applications of quantum computer, and Indian contribution. Then we will public key cryptography and why there is need for post-quantum cryptography. As all of you now briefly know, because of Shor's algorithm, our RSA can be solved in polynomial time. So I will tell you what is the meaning of saying something in polynomial time or in exponential time. I will cover that topic as well. I will discuss about the updates of PQC competition of NIST. Then, as asked by organizers, I will cover lattice-based cryptography in more details. I will briefly touch upon the other directions of PQC as well. So, we all know that cryptography is the study and practice of techniques for doing secure communication in the presence of third parties, which are adversaries. So the goals of cryptography are to provide PAIN, PAI, privacy, authenticity, integrity, and non-repudiation. We all know from the past talks. So the classification is majorly into 2 parts. One is symmetric and public, other is asymmetric or public. So symmetric key allows 2 parties to communicate securely over a public channel only if they have exchanged a secret on a private channel before. And whereas a public key is like, even if you have not communicated privately before, you can still communicate by the help of public key primitives. So it is, however, less efficient than symmetric, and it is based on mathematical hard problems. This is set of some symmetric key is set of some steps which anyone can understand easily. But to understand public key crypto systems, you need to have some background of mathematics. So one thing I want to ask from audience, if symmetric key is efficient in hardware as well as software, then why do we have this concept of public key crypto systems which are inefficient and very slow? Can anyone answer?
Key sharing
or key exchange in the public domain.
Yeah. Because when you have to communicate, you have to share the secret key and this secret key has to be shared using the public key crypto system. So therefore, both these are important, right? So initially you will have some public key in your protocol, then you will have symmetric key. Right, this is the figure that you already know, that the same key is used for encryption and decryption, and different keys are used for encryption and decryption. Right, so other classification can be like classical or traditional, which is being used, and other is quantum. Right. So in traditional we have symmetric and asymmetric. In post-quantum also we have symmetric and asymmetric. But in quantum, with the help of quantum computers, we can meet the cryptographic requirements by the quantum key distribution protocol. The quantum key distribution protocol was developed firstly by Bennett and Brassards in 1984. So theoretical foundations are based on that long, and there is quantum secret sharing and quantum random number generators. So in symmetric there are block stream and message authentication codes as well, and some more are there. And in asymmetric there is discrete log problem based on elliptic curves as well as integer factorization problem. These are the backbone of your public key crypto system. But in post-quantum setting, symmetric key remains the same. There is no threat to symmetric key crypto systems. The only threat, as mentioned in previous session also, it is by Grover search, which reduces the search complexity to half I will say square root times. So just doubling your key size will safeguard yourself from the impact of Grover's. So, but what happens with asymmetric is that it is totally broken with the help of quantum. So you need to shift your hard problems instead of discrete log and integer factorization to the hard problems of lattice, code, multivariate, isogeny, hash, and others. So this, let's look at what is a quantum computer. That also it was mentioned that it uses quantum particles. What are quantum particles? Can anyone answer? Like the electrons spinning output. Yeah, photons are also quantum particles. The particles which you cannot even see with any electronic equipment, that can be just observed that it is there, but you cannot conclude that it is definitely present over here. That can be only observed, and when you observe that particle, its position changes, it is destroyed. And the quantum computer uses those kind of particles and quantum mechanics like superposition or entanglement to perform computations and secure your store data. Quantum cryptography provides cryptographic applications using quantum computers, which I have already told. Let us see the history of quantum computing. It is not like this, that quantum computer has been developed in just last 10 years or like 20 years. It dates back to even 1900, initial 19th century. But in earlier phase, it was just in theoretically developing. But later on, in 1980, there was concept of quantum Turing machine based on quantum mechanics, and as I mentioned, Bennett and Brassard gave the algorithm to do quantum key distribution. Then Richard Feynman and Manin, they introduced the concept of quantum circuit, which you can now means you can create quantum circuit on simulator and run it. It is freely available online by IBM and some other agencies also. Then revolution began in 1994 when Simon, which solved the hard problem of hidden subgroup problem. And that motivated Peter Shor to develop a quantum algorithm to solve the problem of integer factorization in polynomial time. So again, there were from 2001 to the list is not ending. In recently, as mentioned, that Google Quantum AI announced the Willow chip, the first quantum processor demonstrating that error-corrected qubits improve exponentially with scale. What happens with quantum computers is that when you are trying to implement something, then the number of gates has to be very limited, because like after 7 or 8 gates, the state of quantum destroys itself. So you need to have some foundations on the number of gates which you can apply. So that is called the circuit depth that has to be minimized. So when you have such kind of processors, then you have some efficiency over that. So these chips, they are very necessary in order to have further developments on quantum computers. So this is the graphical details of what the progress was there in quantum computers, and it includes the recent one as well. So what are the types of quantum computers? Superconductive quantum computers. Superconductive stands for they work in the temperature of nearly 0 Kelvin. Do you know what is the degrees of 0 Kelvin? Minus 273. So at that temperature, these computers work. So first question, is it possible to obtain such kind of very low temperature setting? So it is very costly. So that's why they are headed in the northern part of our globe. So basically in Canada and Greece, countries like these, they have their setup. So similarly, there are different kind of quantum computers. The NMR is nuclear magnetic resonance. They are basically not exactly the quantum computers, but they provide solution to certain kind of problem which is addressed by quantum computers, on which D-wave works. D-wave quantum computer is famously known to solve certain problems of our everyday life with the help of quantum computers. And Rigetti has launched quantum computer for commercial purpose. So the applications of quantum computers: cryptography and cybersecurity, cloud computing, weather forecast, and the list is very long. So there are many applications, but we will focus more on the cryptographic needs of quantum computers. So the BB84 protocol, the cryptographic applications include the BB84 protocol and E91 protocol, random number generator, and quantum secret sharing. These are the applications of quantum computers. So recent updates are like IT Delhi and DRDO, they recently, this is of 26 November, this last month, they have demonstrated quantum key distribution of 50 kilometers via optical fiber. So this was in headlines days back. So India plans to launch quantum satellite in 2-3 years with the help of ISRO. And QRNGs are also being developed in India. And as mentioned, CDAC is also working on development of indigenous chip for quantum computing. This news is from last year. So let's come to public key cryptography. The first realization of public key cryptography dates to 1970s, in which Duffy and Hellman they provided solution for how can one share a key using public key primitives, public key crypto primitives. So there is developed firstly you should have a key pair which consists of private and public. Private is only known to the owner, public is known to everyone. The security of public key crypto systems relies on the fact that certain computationally hard problems prevent the inversion of public map. Do you know any public map which cannot be inverted? Have you seen discrete log? Anyone? If I give you a number to the power something, can you trace back what the number was? Even if exponent is known to you, then this mapping is used in RSA, and if the board was available here, I could explain more. But anyhow, yeah. So, like in what happens in RSA is that you know what the exponent E is. E is known to everyone. And m to the power E modulo n, that is also known. But you cannot find out what m was. This is the difficulty of RSA. You cannot invert the map easily or efficiently. We will come back to RSA once again in our upcoming slides. At that time I will explain in more detail. The core concept is that private key remains confidential while the public key is shared, ensuring secure communication without needing to exchange secret keys in advance. Yeah. So there is this concept of trapdoor functions. Trapdoor means the door opens and you can get inside and it get closed, you cannot come back, right? So with the same kind of intuition, mathematically the algorithm which is one of the famous algorithms is used by RSA. Suppose your integer n is product of two primes, p and q, right? And you know only the integer n. So the best algorithm to find out p and q, as mentioned in previous, was also given. It is generalized number field sieve algorithm. So, but when the number is very large, it is even difficult for world's best computer to find out what the factors were, like p and q. So what happens in encryption? Encryption of any message comes from Zn. So encryption of a message, and your E is a public key. E is chosen in such a way that there exists D such that ED is 1 modulo phi n. Right? So E is your public key and n is known to you. So the private key is, this is the private key. So you encrypt your message with the help of public key. And what the encryption is? M to the power E modulo n. So if this is known to you and E is known to you, then you cannot find what M was. This is trapdoor. Means you can compute, but you cannot go back. You cannot invert. So this is the logic behind any public key crypto system, that you can easily go from domain to your range space, but you cannot go back from range to your domain space, right? So one example is this. This is used by RSA, and there are many other public key crypto primitives which are given by lattice, code, multivariate, and isogeny. The thing is that this algorithm of RSA relies on the fact that n cannot be, the factors of n cannot be computed easily, right? But the Shor's algorithm provides us efficient algorithm to find out these factors p and q easily. So one has to look for other hard or trapdoor functions. So here I am mentioning again what is polynomial time. So let us look at in more detail what are these. When do we call something as a polynomial time or exponential? So running time of an algorithm refers to the number of operations required to execute that algorithm. If I give you two binary numbers of say length 10, then you have to add those two numbers. How many operations will you require? Yes? If you have two binary numbers of length 10 each, then how many operations you will require to add those two numbers? 10? Yes. But what if I give you some complex operations to perform? Then you will see your algorithm, how many steps that is using. Then that number of steps is basically your running time of that algorithm. Here, for example, 10 was this. So it depends upon the algorithm which you are following. Because in mathematics, what happens? We all might have experienced that in school times, our teacher used to give a solution by some other way, and in exam we did in some other way, and still the results are correct. So teacher gives us marks. So why is it so? Because in mathematics, there is we cannot say that there is only one algorithm to some problem, addressing some issue. So different algorithms are there to solve particular problem. So for each algorithm, you can compute its running time, and that running time depends on the algorithm. So the lesser the running time, the more efficient that algorithm is, right? So if I give you a number of 10 digits and ask you to find its factors, so what strategy will you follow? You will start from 2, you will check is 2 divisible by this, then you will check 3 is divisible by this, then you will check 5 is divisible by this, 8 or 7 or 11 and so on, right? So, and you will go till under root of that number, ideally. This is one of the algorithms. But is it efficient? It is not efficient. So the best efficient algorithm to factor is this generalized number field sieve. That takes minimum efforts to solve the same problem. But still that algorithm is not very efficient when n is very large. So the running time depends upon the size of your input as well. If your input is like 100 bits, then your the running time will depend on those 100 bits. If your input is of 200 bits, then obviously running time will be more. And other is space complexity. In order to execute algorithm, you need to store some, compute something and store it and reuse it when required. So space complexity is also equally important as time complexity. So if you you have your computers having 128 GB of RAM, and you are executing one algorithm on that computer, in which while running that algorithm, you have to use more than 128 GBs of memory, then that algorithm fails to run on that computer. So that's why space complexity, to check how much resources are required for memory requirements are required for that algorithm, that is also important. So the mathematicians working behind cryptography, they study both the running time as well as space required by that for some algorithm. Because if it takes like 100 TBs of data to run an algorithm, then it won't be that good, right? So lesser the space required by an algorithm, more efficient is it. So there is always a trade-off between running time and space. So this we call time-memory trade-off algorithms. So there is one notion, big O notion. Any function is called big O of g if f is always less than equal to some constant times g for sufficiently large values of n. So these notions are important when you are studying the time complexity of any algorithm. So if f was this and g is this, we say f is big O of g because f is always less than equal to g when n is greater than equal to 5. F is less than equal to c times g when n is greater than equal to 5. So we say that f is a polynomial. F is big O of a polynomial of degree 3. The higher the value of exponent is, the more bad that algorithm is. So the efficient algorithms mean having the smaller exponent. So if f is any polynomial of degree k, then we will say f is big O of n to the power k. And if any polynomial is of order e to the power n, e is exponential, right? Or here there can be any constant greater than 1, then we call that polynomial as exponential polynomial. So if the number of steps involved in any algorithm is given by fn, then we say that that algorithm has complexity cubic in this case. So running time is cubic. If the number of steps involved in running that algorithm is given by fn, then we say that that algorithm has the cubic complexity. But if any algorithm has x to the power n number of operations involved, then we call it as exponential running time algorithm. So we say any complexity of any algorithm is polynomial time if the number of operations when expressed as a function is a polynomial in the size of input parameters, then that algorithm is called polynomial time. The same when we compute the function turns out to be exponential, we call it exponential time algorithm. And sub-exponential involves both the product of the exponential term and the polynomial term. Actually, log n denotes the number of bits of any number. So, and the sum of these exponents should be equal to 1 in case of sub-exponential. So which algorithm runs efficiently is polynomial time, worstly is exponential time, and in between is sub-exponential time. So the generalized number field sieve is sub-exponential time algorithm. It is not very bad, it is not very good, it is in between. So we have this concept of polynomial and NP problems, P problems and NP problems. The problems in P, the decision problems, like if I ask you, given any 10-digit number, I ask you, is this number prime? Yes or no? So to solve this kind of problems, we have this class of NP problems. The problems, I will demonstrate this graphically as well. The problems in class P are those decision problems which have a solution whose running time is a polynomial. Polynomial I just mentioned. the algorithms which have running time as a polynomial of input parameters. So, like given a number, and you have to just answer yes or no if n is prime. So this can be done in an algorithm which is polynomial in the size of input, and by the algorithm given by AKS. Do you know what stands for AK and S? Anyone? A hint is first one is the director of IIT Kanpur. Yes. First is the director of IIT Kanpur, Maninder Agarwal. Second is Kyle. And third is Saxena. So they were BTech students in IIT Kanpur in 2004. They developed this algorithm which was revolutionized, because earlier there was no such algorithm in polynomial time that could determine if n is prime or not. Then comes the problems of class NP. Those decision problems in which saying yes is polynomial, but whose yes instance can be verified in polynomial time, but no instance cannot be. You can say that all the problems in class P are also in class NP, because their yes instance can be verified in polynomial time. Means if you say that n is prime, you said yes, n is prime. Means you are giving one algorithm to check that n is prime or not. And that algorithm, so yes instance of that problem is verified in polynomial time. That's why all the problems in P are in class NP. But not all problems in NP are in P, right? So this was a revolutionary problem of complexity, that P is not equal to NP. So what are the problems of co-NP? The decision problems whose no instance can be verified in polynomial time. So what all problems are in NP that are not in P? It includes NP complete problems. So a decision problem is called NP complete if solving that problem in polynomial time solves every problem of NP class in polynomial time. Means it is as difficult as all NP problems. What problems are there? One example is subset sum problem. You are given a set of natural numbers and an integer s. You are asked, is s a sum of some elements out of these set? How will you do this? I am giving you, suppose, 100 integers, positive integers, and I ask you, is the sum of some numbers equal to 50 or not? How will you do this? You will look at all possible subsets and try to see if 50 can be obtained by some of those integers. It's very difficult. So this problem is not a problem of class P, right? Because it has no solution as of now. In future, maybe there can be some genius who can develop an algorithm to solve this problem in polynomial time, but for now there is no. So what are NP hard problems? A decision problem is said to be NP hard if solving that problem solves all the problems of class NP complete. Means it is as difficult as every problem of NP complete. So what are those problems? Computational version of these NP complete. Firstly, I was asking, is there any subset whose sum is equal to 50? Now I am asking, determine that set. Right? So the computational version of all the problems of NP complete, they are NP hard problems. So the post-quantum crypto systems, which are lattice, code, multivariate isogeny, they all have their hard problem lying in NP complete and NP hard. That's why those crypto systems are still secure. So this is the geometric or graphical interpretation of how the complexity of complexity classes are there. We have this set is NP, set of all decision problems whose yes instance can be verified in polynomial time. Its subset is the set of problems lying in class P. Then there is this NP complete, and NP hard can be non-decision. That's why it is not intersecting NP. Right? This is what the previous definitions also said. So hard problems, as I mentioned, integer factorization, which is used in RSA. Is it NP or NP hard or what? Integer factorization problem is not proved to be NP hard problem. Right? It subsets some problem that is NP hard. So there are many other problems which are proven to be NP hard. So we have to make use of some other hard problems for our cryptographic requirements in post-quantum scenario, because this is gone. So what is the current status of cryptographic requirements across the globe? Two widely used public key crypto primitives are RSA Diffie-Hellman, you can say elliptic curve Diffie-Hellman, and for digital signatures, RSA elliptic curve digital signature algorithms, they are being used. So this is one where I was trying to explain what RSA is all about. So why to worry? The impact of quantum computers because of Shor's algorithm, the integer factorization problem for integer n can be solved in, this is polynomial time algorithm, because log n represents the number of bits representing n. So I told that what are polynomial time means any function which is a polynomial in the size of input, and here log n represents the size of input. So this is the polynomial time running algorithm, and I also mentioned that polynomial time running algorithms are the efficient ones, therefore this is efficient. The catch is that it runs in quantum, it requires quantum computers, as already discussed. So what about elliptic curves then? In 2003, Proust and Zolka, two people, they proved that elliptic curve hard problem can also be solved using quantum computers by using the similar strategy as Peter Shor's. So that is also gone. So key exchanging and digital signatures are gone in the context of quantum computing. But we all saw that quantum computers, they are getting better and better every day. So what about symmetric? So there is algorithms which are being used, AES, and somewhere triple DES is also used. And for integrity, SHA-2, SHA-3 are being used. So what are the impact of quantum computing? By Love Grover. He is Indian, and he has been graduated from where? From which Indian institute or university has he been graduated? Do you know? He is alumni of IIT Delhi. So he said that if n-bit size is our key, then we must require 2 raised to power n number of searches, but instead of 2 raised to power n number of searches, that search can be done in 2 raised to power n by 2 number of steps. And with this, our search complexity reduces to half. So what can we do? We can just double the size of our keys. So doubling the keys of symmetric key crypto systems, that can be done easily, because when AES 128 came, then at that time AES 256 was also there. So we will migrate all our requirements to the next updated size, and we can safeguard ourselves. And in 2015, Michael Mosca, he gave one very interesting fact that suppose you have to keep your data secure for like 10 years, and your cryptographic migration time is also 10 years, suppose. And within those 20 years, if quantum computer enough capable of breaking that crypto system comes into like practice, then your all the secret keys will be revealed. So you have to, but you don't know at which moment quantum computers can come. Like suppose tomorrow there comes a quantum computer that can easily break RSA 2048, which is being used. Then what will you do? You don't have enough time to migrate all your RSA requirements to your post-quantum crypto systems, right? So that's the purpose why we are working on post-quantum cryptography, because we don't know when quantum computers capable enough comes. So we have to we actually in 2015 around time when the NIST started their PQC competition, at that time it was realized that by 2025 there will be large enough quantum computer that could solve RSA problem. So by 2025 NIST wanted to select some post-quantum crypto system for standardization. But now they have extended this deadline to 2030 by observing that still we are lagging behind our quantum computers. So what people say that migrate your cryptographic primitives on computational hard problems that quantum as well as classical computers can't solve efficiently. So that's why we have this concept of post-quantum cryptography. It is important to study right now because no one knows then that when can be there a high demand of post-quantum cryptography, the key size, but not the public key. So we have many verticals. The most prominent vertical are these: lattice, algebraic codes, multivariate polynomials, isogeny, and hash. Some of the example candidates lying in these are mentioned over here. NTRU was one of the most prominent candidate of lattice. However, it has not been standardized by NIST. The Kyber was selected as finalist in the third round. Presently, round 4 is going on, and there is additional call for digital signatures also going on. So, coming to the NIST PQC standardization, it was launched in 2016, and they called for globally they called for papers which address the public key crypto systems whose hardness relies on a difficult other problem than RSA, and which remains secure in the sense of quantum computers as well. So there were 69 algorithms which were submitted in the first round. Then after the initial evaluation, many crypto algorithms were discarded. Either there were attacks on those or they were not lagging of security proofs. So in the second round, 26 algorithms moved ahead in that competition. Then few algorithms had already been discarded due to vulnerabilities. In the third round, there were 7 algorithms which were selected as candidates for finalists. Till that time, Kyber was coming into highlight, and the selected candidates were announced in 2022. They were declared as winners: Kyber, Dilithium, Falcon, Spinix Plus. And in 2023, the winners, they were asked to prepare a formal report document of their design, and in 2024, that design was released. The alternates on the final round, that is round 3, they were based on coding theory, byte, HQC, classic MacLeese, and one isogeny based crypto system was also there, Psych. But very soon there was attack on this Psych. So they were all like puzzled, how can there be attack on such a prominent candidate. So that made them call for additional digital signature schemes in 2022. And as mentioned in August this year, they released the documents of the 3 winners of round 3 competition: Crystal, Kybers, Dilithium, and Sphinx. So for additional call for digital signatures, there were 50 submissions in 2022, and in this year, 2024, the second round held, and in which 14 of these out of 50 moved ahead. And we saw one new approach instead of lattice code, multivariate isogeny symmetry, and hash. There was MPC-ITH. This stands for multi-party computation in the head. There is one nowadays coming more trending research direction in cryptography, is that suppose you have your plain text, but you don't have that computing facility, that large computing facility on which you can perform your computation. So you outsource your computation to some other party, but you don't want to reveal your plain text. Then what we do is we encrypt our data, we send them the ciphertext, they perform the computation on the ciphertext and give us the result. And the result which they give us, we decrypt it and get to know what our function would have given us. But the point is, this encryption must be homomorphic. Sorry. So there is this concept of fully homomorphic encryption. So fully homomorphic encryption schemes are getting trending these days. And trust me, last week I visited Asia Crypt in Kolkata, and out of 127 accepted papers at Asia Crypt, majority of them were based on fully homomorphic encryption, and it is trending these days. So coming to the first category, lattice-based crypto systems or cryptography. So what is lattice? We are given some linearly independent vectors from Rn. So how many independent vectors can we have in Rn? Maximum? Yes. Do you know any basis of Rn from linear algebra? E1, E2, En, standard basis. So basically, firstly I would like to highlight is that these all are mathematical topics. So Rn has n, can have n many linearly independent bases. So, but that basis need not be unique. There can be many n independent vectors. So we take one set of independent vectors from Rn and define a lattice on that independent vectors as the integer linear combination of those vectors. So that integer linear combination is represented by these discrete dots. These kind of discrete dots are the lattice, is called the lattice. So in R2 it can be represented by this dots, and the set B is called the basis of that lattice. So these lines, these are vectors, the one which we are already studied. So first hard problem in lattice. You are given a basis of any lattice and you are asked to find the shortest vector of that lattice. shortest vector means you are given a plane and a set of discrete points, and you are asked to find the closest lattice point to origin. For example, in this case, it can be visualized that this point is the nearest to origin. But if I give you some bases, you will not be able to find out what the shortest vector of that lattice is in polynomial time. So there is no efficient algorithm to find out the closest vector of any lattice. So this can be visualized easily in the case when n is equal to 2, that is this plane is R2. But when this dimension increases, then it is very hard to even visualize, right? And given any basis, you can, means in this case, if you are given this set of the points as basis, then it is easy to visualize how the points will go. But when given very closely related basis elements, like the angle between these two is very small, such kind of basis is called bad basis. When the angle between the basis vectors is very small. So in that case, you cannot get a good basis. So this is the hardness of shortest vector problem, and this problem is considered as NP hard. So SVP is used as a backbone of NTRU crypto system. So second is closest vector problem. Supposingly the same lattice is given to you and you are given a target vector. Target vector can be, it should be non-lattice vector, non-lattice point I must say. So, and you have to find out the closest lattice point to that, right? So it is somewhat similar to shortest vector, but it is not exactly equal to the shortest vector problem. Actually, it is more harder than shortest vector problem. You are given a lattice and a target, and you are asked to find the closest lattice vector to that target. So this problem is also NP hard. So the third one is learning with errors problem. So what you are given, some vectors of zp to the power n. Zp represents the integer ring of integers from 0 to p minus 1 under modulo p operation, and n tuple over that. Yeah, and you are given m of those. Other than this, you are also given some inner product with a1 plus some error, and some inner product with a2 plus some error, and this s is kept secret. And E1, E2, EM, they are Gaussian distributed with standard deviation of alpha p. The point is that you have to find out what the secret S vector was, given m many inner tuples. So this problem was introduced by Oded Regev in 2005 and was shown to be as hard as some variants of SVP, shortest vector problem. So this problem is very hard. Why am I telling this? Because the crypto systems which have been standardized by NIST, they are based on certain variant of LWE problem, learning with error problem. In fact, that is module learning with error. So, but if there were no errors in this, that can be easily solved by solving the system of linear equations, which can be done by Gauss elimination method. So the errors play a very important role. So the ring, there is ring version of learning with error problem. You replace your ZP with some polynomial ring, and module you replace your again that ring with certain modules. If you have studied commutative algebra, then you would have learned what is modules. Modules are basically kind of vector spaces over rings. So firstly, in order to learn what is module learning with error, you have to learn what is LWE problem is and what are modules. Then this is very easy. So the time complexity of solving MLWE is exponential. So there is no efficient algorithm to solve the problem of LWE. The problem is to find that secret vector S, the same which was in LWE. So as I mentioned, LWE was introduced by Audrey Regev, and the first public key crypto system was also designed by him. And why am I more focusing on him? Because he is a prodigy in cryptography, because he did his PhD in the age of 21, and he is professor at either MIT or Harvard. So what the crypto system based on LWE look like? You have sampled a vector from ZQ or ZPN, and you have a matrix, and you have error coming from Gaussian distribution. So Gaussian distribution is basically centrally distributed normal distribution. If you know its graph is bell-shaped. That bell-shaped graph, but that is over real numbers. So here it is over ZQ. So it has to be firstly brought to integer Z, then it is extended to over to ZQ. And you compute AS plus C, that is known to public, B, and A is known to public. But the point is you have to compute S. So this is again a trapdoor. You can compute you can encrypt, but you cannot decrypt unless you have access to S. So the encryption scheme is also described over here. The same is expressed over rings and modules, and over modules is our crystal Skyber. So crystals stands for cryptographic suite for algebraic lattices. The authors include these, and dilithium is also part of crystals. So its authors are described over here. And at AsiaCrypt, Vadim Lubashevsky and Devin Stell were the most prominent figures. So what is the crystal Skyber public key encryption? It is based upon the polynomial rings R and RQ, where ZQ denotes the integer modulo prime, P or Q is 3329 prime. So the key generation algorithm of crystal Skyber is same as the LWE algorithm. How much time do we have?
5 minutes.
Okay. So actually I was asked to deliver more details on crystals. So
Yeah, it's okay.
yeah. So it is actually similar to what LWE based crypto systems are. And the encryption is also same. I think in evening session you will have a hands-on experience on how the encryption works by not considering the compression and decompression functions which are mentioned over here. When you remove these, you have a direct algorithm of LWE based crypto system, and that will be shown in the demonstration. So again, the crystals dilithium, that is digital signatures, that also uses R and RQ, and its key generation, signing and verification algorithms are also not that hard, but you have to firstly learn what LW is, modules are, and then you already know what are digital signatures, how they work, and the process is not that hard. Next candidate was code-based cryptography, on which I am working on. That is based on the hard problems of decoding random linear code, which was proven to be NP hard in 1976 by MacLeish, Tilburg, and Burlingham. And MacLeish gave one algorithm in 1978, the same time when RSA came. But that candidate was not selected as a publicly globalized candidate because it was not efficient. But as there is attack on RSA, there is no attack on code-based crypto system given by McLeish. So it is in the candidate of post-quantum cryptography. So the alternate candidates or the candidates in round 4 of this PQC competition are classic McLeish HQC and Bike, which are based on hardness of decoding random linear codes. But there are some attacks on code-based crypto systems when the code structures are very algebraically good, which includes Reed-Solomon, Reed-Muller algebraic geometry. For coding theory, I will like to mention one very interesting point. The QR code you scan everywhere. You know that QR code is the code which is coming from coding theory. That is, its full form is quick response, but however, it is based on Reed-Solomon codes. And also, all the satellites which are like being used, they also use the concept, the class of Reed-Muller codes. So they are very important and very widely being used codes, and these have attacks when they are used in cryptographic setting. So the third was multivariate cryptography. In this, you have to solve a system of polynomial equations. Even if when you have a system of linear equations that you can solve, but here, if you are given a system of polynomial equations and the degree of polynomials, even if that is 2, so that's why it is called multivariate quadratic polynomial. So if you have polynomials of degree 2, then also you cannot solve this system. So this hardness is established by, if you have an algorithm to efficiently solve this, then you can solve one of the most famous problem of satisfiability problem. The other one was isogeny based crypto systems, and these rely on the hardness of finding isogeny between elliptic curves, which is also proven to be NP hard. So with this, I will like to end my talk. If you have any questions, you can discuss.